So with circuit diagrams here, you need a path for this electric circuit to occur. So for example, even in an MP3 player, you've got circuits to enable it to play the music, because the speaker would be the part that's the output and the battery would be the input energy. So the things you need for this to work is a source of energy, as I said, which would be the power supply, or in this case the battery. Some sort of a component to use that energy up, which could be a range of things from speakers to displays to motors and so on. In this case, it's mostly the speaker. And you need a complete loop for this to work, a complete circuit or a complete circle, and you need to avoid short circuits. Okay? Now, electronic circuits are normally very complex. They're not just simple ones with just a few parts I've just shown you. They can have as many parts as this here, that's part of the computer. So when you're trying to draw a circuit drawing of that, you're better off using symbols and drawing a diagram, which makes it easier. So there are certain components that you can actually use, or symbols for these components you can use to show the circuit diagram. So in this case here, they usually use copper as the conductor that actually takes the charges around the circuit, and it's coated in some sort of insulator, like a plastic, to actually stop it from short circuiting. Okay, that's the plastic sleeve there. And a symbol for that would be just a conductor, or a wire would just be a straight line. So this remote control uses a cell, and so a simple dry cell just has a long tall stick, I suppose, and a shorter, fatter one. The long tall stick is the positive terminal, and the short one is the negative terminal. And the circuit symbol for battery, you could draw multiple cells alongside each other, but sometimes they join up with a dashed line there to show that it could be any number of pairs of cells making up a battery. And it's obviously producing some sort of a voltage or potential difference there to supply the energy. Now switches, they will actually break the circuit there, so you make an open circuit so that there's no complete path, and therefore the electricity would stop. Okay? So that's your first bit, either an open switch or a closed switch. If the switch is closed, this lower one here, you'll actually find that it's on, and if it's open, it's off. A globe there could be called a lamp or a bulb as well. There's a range of different types of those, and one of the new ways of expressing that is with a symbol with a circle with a cross in it. A resistor, we can just draw a rectangular box there. Sometimes I'll have the numbers in it to show you the resistance. And the arrow means you can adjust the resistance, and it's adjustable. And the one we've got at school looks similar to this, where you've got a length of wire, and you can change how much of that length of coil of wire you use by moving this slider backwards and forwards. Okay. You can measure the current with an ammeter to measure the amps. This is a digital ammeter. Or you could use the voltmeter to measure the voltage. In this case, this particular one would do voltmeter with digital as well. We actually use analog scales for ours in the lab. There's a range of symbols there you can actually sort of look at. Current will always pass along the path of least resistance in a circuit. Okay. There are things that have more resistance than others. The ones with very, very high resistance would be insulators, non-conductors, so they would not conduct electricity. So with the symbols here, you can draw the circuit diagram. So if we just test a few of these things, which circuit diagram shows a complete circuit here? Well, A's got a gap in it, so that's not right. Now C, that's actually a complete circle, but it's missing something to make it a complete circuit. It's got no battery or power supply, so you would go for B there. Okay, is the correct answer. Which circuit contains a variable resistor, so that's one you can adjust. It's that one with the arrow on the right-hand end here. Okay, that's the adjustable resistor, or variable resistor, sometimes called a rheostat. Which circuit contains a lit bulb? C won't work because there's no power supply. A you'll find is a short circuit, which we'll talk about later here. The electric current would rather go round through the first circle and not go down through the globe, because the globe's got more resistance. So this one's the lit one. Okay. Which circuit contains an open switch? So that would be C. And which circuit contains a battery? That's the one where there's more than one cell together. You're looking for A. Okay. Which circuit contains a short circuit here? That'll be this one here, because you'll find the globe will be bypassed and the globe will go off here. It will just take that short path, or the path of least resistance. Okay. Now, there's a couple of key things to get right in electric current and voltage and circuits. The current tells you how much the rate of flow of charge is going on. So it's measured in amps. Okay. So that would basically be based on how much charge flows per second. So charge is measured in coulombs after Charles Coulomb, and you're looking at how many charges per second. And I'll come back to that in a minute. And you measure an ammeter placed into the circuit in series, positive terminal to positive terminal of the power pack. Okay. If you're measuring potential difference or voltage, it's measuring how much electrical energy is being given per charge, and this is also called the voltage, and that's measured in volts, and the voltmeter must be connected around in parallel inside the circuit. And again, the positive side of the voltmeter should end up to the positive side of the power supply, otherwise the needle will go back. So you can use water as an analogy to compare what electrical circuit does. So what we've got here is a water pump dam on the side here, on the left. That's going to pump water up and give it energy to go up the hill, so then come across and come back down the other side and passes energy onto this water wheel, which is very much like a battery or power supply supplying energy on the left and some sort of component using energy on the right there. Okay? The water acts like the conducting charged particles there in a typical electrical circuit, and you can see the pump there is the energy source providing the energy to lift the water up to the top there. This turns the wheel, which represents the component. The height differences also represent the change in potential energy, which we can think of as being linked to the voltage. The pump moves the water to a higher level, increasing the water's potential energy, so that gives it that push, which could represent 12 volts in an electrical circuit. When the water turns the wheel, the water loses energy, and that sort of shows the potential energy drop there at the, I guess, the water wheel in this case, but the globe in the case of electrical circuit. And so potential difference in voltage, you can think of being the same sort of things, okay, in measured in volts. This water fountain analogy that I showed to you in the last clip has just been done a bit neater here. The water's pumped into the air by the pump, and it's supplying energy to each bit of water to push it out, and it comes out to a higher level depending on the size of the pump. The larger the pump, the higher the level will be. That's very much like the electrical circuit. You've got a power supply that might be supplying 12 volts. This equation shows you it'll give you 12 joules of energy to each coulomb of charge, and that will give you the energy, the push around the circuit for each individual charge. The current that's involved with that one, measured in amps, is the quantity of charge in a given time. So it's the rate of flow of charge, much like it's the rate of flow of water in litres per second in this fountain analogy. Okay? The resistance, measured in ohms, measures how much it's going to resist or hold back that current. So if you had a very high voltage producing a very small current, it would show here that you get a very large resistance from that formula, R equals V over I, which is known as Ohm's law. The resistance is the voltage divided by the current, and you can rearrange that to different forms. So let's have another look at conductors and insulators here. In some materials, electrical charge, they're not free to move, so there's no current flow. So they would be in the cases of insulators. But when there is a current flow, you've got those going through conductors. They're materials that will actually allow charge to flow very well, and they tend to be metals. Okay? Insulators are non-conductive materials, as I've just said. Plastic's a good example of an insulator. The typical metals then, they tend to have 1 or 2 or 3 valence electrons in their last shell. So when you look at a metal lattice there, they tend to have electrons free roaming between the ions there, and so they'll be moving in a random pattern there. And if you do your chemistry, you'll know that there's free electrons in typical metals. So these are obviously easier to sort of set up a positive end and a negative end and cause the electrons to be attracted towards that positive end, and they'll drift in one direction. And they'll be good conductors. It turns out that there's lots of collisions that these electrons undergo with these atoms and nuclei, and that actually keeps knocking them backwards, but they will steadily drift towards the positive end there. So they'll be good conductors. As it says there. Insulating materials do not contain free electrons, and so current is unable to flow. And you can get ionic solutions that also conduct electricity because they've got free ions available to carry the charge there and cause current flow. A semiconductor, of course, has just a few electrons in, so it will conduct, but not as well as the metals will, the really good conductors. You can do an experiment with that where you drop different things into a circuit that I've showed you before. So if you were to try something like sodium chloride solution there, and place that in there and turn on the circuit, you will get that to conduct. Okay, because the ions of sodium and the ions of chloride are free to actually pass it around, and you complete the circuit. Now let's have a look at the direction of current. This is an old one. Over a couple hundred years now, they've been looking at electric currents being positive. That was a decision they made when they first set this up as a convention. So they assume positive charges are in the wire, so conventional current is always drawn as going away from the positive and around towards the negative. All right? That's called conventional current, and you'll still see that in all books across the world. In actual fact, we now know that it's electrons, which we didn't know about before, which is moving around So they're going to go in the opposite direction from the negative terminal away in the opposite direction. So just bear in mind that conventional current is one way, which is what they sort of use all their diagrams with, always assuming positive charge. But the reality is, it's electrons that really flow around the solid, and that goes the other way around. But you'll see all the diagrams shown in the books using conventional current. So finally, the last sort of practicals you're going to do is to look at series and parallel circuits here. So the series circuit is like a comedy series. It means one thing after another. It's got one path. There's no deviations. You've just got the one event after the other. So think of it as being one path connected on a single loop. Okay? So Christmas tree lights traditionally used to only have the one path there, and if one of those globes blew, they would all go out for the one path. They now got them wide, a bit more complex, and if one of them glows, you'll get a set of it going out. Whereas a parallel circuit contains junctions, and so there is more than one path for the current to follow through. And that's what happens in car headlights. If one of these was to blow, then you'll find that the other one doesn't blow. Alright, so let's look at investigating some series circuits. I've put three cells back to back in here to give you a total of 6 volts, which is 6 joules of energy to every charge. If you close this off with just one globe there, and we might put an ammeter in there as well, I think, you're getting the same current of 0.9 amps on each side. What do you think happens if you put a second globe in there? And try this again. Now the current here has gone down. The brightness has gone down a bit. And you can see this current's gone down. And this is more than likely because the resistance has gone up in the circuit. It's hard to get through the 2 globes. If you go to 3 globes, and we try this again, and you'll notice that all these globes are off at the moment because of the one switch. All of them are involved in an open circuit. To close it, these actually, I don't know if it shows up there, but they're a bit duller again, but the current's gone down again because the resistance is even higher. So as you know, globes in a series circuit, the resistance is going to go up, so the current's going to go down. You should also notice that the current's the same all the way around the circuit, because whatever current's flowing through here, the same electrical current, charges per second, is flowing through here, and so on all the way around. And one switch would actually turn them all off in one go. A typical series circuit you could draw like that and expect the current to stay the same. You can measure the voltage across the series circuit here by putting a voltmeter around each of the globes, and then you can also check it across the power pack and compare the voltages here with the total being released here. As more are added there, you'll find more voltage is being used across each of the globes, but the total voltage coming out should equal the total voltage as you add them together across those globes. So if we look at parallel circuit here, and again we put in some 3 cells to get this going, and we'll try putting a second bulb in now, see what it does. You should find the globe staying very bright with 2 globes there compared to 1. There should be no loss in brightness there. If you put some ammeters in there, and we'll try this again, what actually happens when the currents get into here is the charges are splitting and separating into 2 directions. So 1.8 amps as a total is due to 0.9 amps going down this particular pathway and back again, whereas the charges that go down here and come back round here will also produce a 0.9 amp current down here. So the total current has split in 2 directions to give you 0.9 amps down each of those pathways, and you get a larger current. If you were to add a third globe in there and do the same thing here, you still get 0.9, 0.9, 0.9 down individual paths because the resistance down in each path is the same. And they still stay very bright then because of that. They've each got the same brightness. The total current has gone up. It actually adds up to these. And you can see that that current must be splitting as it comes down here. So if you compare the voltage here then, there's a 6 volt cell package here, or 6 volt battery there because you've got 3 cells put together. They were going to supply 6 joules of energy per kilo of charge. So 1 kilo of charge that comes down here gets to the junction. When it comes down this way, it only passes through 1 globe. So where's it going to use all 6 joules of its energy in? It's going to supply it to this 1 globe here. So this globe gets the whole 6 joules of energy, and it's got a current of 0.9 amps going through it. And that's the same as it was when there was only 1 globe in the circuit. Any charge that come down this particular part of the path only pass through 1 globe. So again, all 6 joules of energy at that globe there. And again, the current's 0.9, and the same with the last one. So you can keep adding these like in a parallel circuit in a house, and you could even put switches on each individual path here to turn them on and off individually. So parallel circuits are really good because they don't lose their brightness the more globes you add, and you can also have a switch there on each path to turn them on and off individually, and they don't affect each other. But again, as I said, you could add 4 5, 6, 7, 8, 10 globes, but the total current would go up and up. And obviously in the classroom, you could actually end up bigger than 5 amps, and that would blow the ammeter. Typical parallel circuits can be drawn like that. Then you can see here you've got an ammeter measuring the current down each of those pathways, and at the start and at the end before and after the branching. And you can also represent it like this, with some voltmeters in there to measure the voltage across there to see what the voltage is doing. But as I said, the voltage here should be the same as there and the same as there. It doesn't split up at all. And they'll be nice and bright then because of that. So the total resistance you'll find goes down in a parallel circuit when you add more and more, whereas it goes up in a series circuit.